Okay, hello everyone. So I think today's lecture just continue for a little while. So this is, I forgot to mention how to practically find the rank matrix. So basically the rank can be found through the row operations. Okay. So for example, uh, so there are some theorem here, but I would like just to emphasize the last theorem. It says that the rank of matrix A, it could be the same as the number of non-zero rows. Okay, so basically, if you are going to evaluate a matrix, okay, for example, you see this matrix here. If we can take some row operations and we can show that because there is one row that all zero, so we have two rows that is non-zero. So we could just determine that, okay, because there is non-zero row, there is two, we say that the rank of this matrix is two. Okay. So this is actually the emphasis from what we had before, which we call how to take the row, set of rows, that we could make it into linear dependent or linearly independent. So instead of taking some actions to make it zero, we could just make it into our row operation. Okay. So we are going to try to make out the last row as zero. If we couldn't, like for example this last part here, we have 3 by 3 matrix, but the last row somehow it cannot be zero. So we say, okay, this will be the full rank tree, matrix tree, rank matrix tree. So that is how practically we can find the rank. So I think this row operations will be the basis on, I think if you want to learn more on the linear algebra, then one way to solve is using this row operations, and the whole thing using row operation. Okay? So this is just a quick note how to use the row operations to find a rank. And basically, a rank in practical meaning, it doesn't really compute or apply anything. It's just a tool to analyze whether the solutions is consistent, inconsistent, and so on and so forth. Okay. I think that's the just a small note. But today I would like, if we have time today, I would like to continue. First is determinants and show how it works if you haven't learned before, especially 3 by 3 matrix determinants. And then after that, I will go into introduction of the inverse. Okay. So a determinant is important, especially to find the inverse of matrix. And inverse is important to find later on when we learn about the eigenvalue and eigenvectors. Okay? And those are special keywords for solving system differential equation. Okay? So we are going to, like I think I mentioned a week or 2 weeks ago, that our goal is to be able to solve a differential equation, which we have done before, but now we are going to try solve it using matrices. Okay. So this is rank. So as I think I mentioned this also. So last time I mentioned about the determinants. So I would like to emphasize the 3 by 3 matrix determinants. Okay. I think determinant 2 by 2, most of you are familiar with that. So 3 by 3 matrix, we could write using this mechanism. Actually, in your textbook, there are some notes that I think I will just skip that notes. I will just focus on the how to practically working on the determinant. So basically, we can write this coefficient. This is based on the first row. So first row is A11, A1, A13. Okay. And basically how we are going to deal with this is, if we start the A11, it means that we are going to to cover this row and cover this column. So we are having this determinant. Okay. So we have A22, A23, A32, A33 determinant. Okay. We multiply. And then for A12 we have this. We have A21, A31, A23, A33. Remember, in matrices, there are some special rules that we need to have a negative sign. And then we plus again A13, the same thing. We cover the row and cover the column, and we have this as determinant. And then we work all these 2 by 2 determinants, and then multiply and then compute. And that's basically how we get the 3 by 3 determinants for the matrix. It will work well with 4 by 4, 5 by 5, 6 by 6, and so on and so forth. It's the same pattern. So another thing about the signs, we have positive, negative, positive. This is what we call, if you see the matrix terms, that is, we call the cofactor. But I don't want to use that term because I think sometimes it might be confusing. So I will just practically apply the computation directly. So basically, let me make it smaller. So if we have the A, 3 by 3, for example. Now, if we take the A11, it will be positive. The A12 will be negative, positive, negative, positive, negative, positive, negative, positive. And how to apply this? Basically, we could apply the same determinant, but with different coefficient. With different coefficient, but it will result in the same determinant. So for example, if we state the second row, so this is the first row. So let me write here that this will be the first row using first row. Okay, if we using the second row, for example, the determinant will be, we are going to start with the negative. Okay, so negative A21 multiply with the A12, right? A13 and A32, A33, and then plus the A22. So A22 we have A11, A11, A31, A13, and A33. And then lastly, it's negative A23. This will be A11, A12, A31, A32. Okay. Now the choices, how we choose the rows, sometimes it depends on our preference. But for example, if you see the matrix and you see some point in the matrix, some in the arrays, maybe they have 0. So we can use that, because if, for example, if the second row, maybe they have 0 in the middle or maybe in the left, then one terms will be 0. So we have a shorter computation. So that's how we can choose. So it's not always the first row. We can choose first row, second row, or third row. It depends on our preference. Maybe if you prefer to have a short calculation. But don't forget the signs. Okay? Don't forget the signs that they have a pattern in the signs. We call this the cofactor. So we have the cofactor, we have the coefficient. Okay? And there are actually some formula, but I think the formula it doesn't really needed here, as long as we know the pattern. And if we have like more than 3 by 3, the pattern still holds, but imagine if you have, like, for example, 4 by 4. 4 by 4 means that you are going to anticipate that there will be 3 by 3. If you, for example, let me just draw a 4 by 4. If you want to calculate this, let's say finding this determinant, it is workable, but I think it takes time. For example, we have this. So we're still using the same pattern like this. So we start from here, positive, negative, okay? And the way we do it is practically the same. For example, we see this is 0, right? This is 0 and 0. So I think the 4th row has a shorter calculation. So we can use this 4 row. What it means is that we are going to first is we cover this part. So we need to find this determinant. So maybe the better way to solve this is we calculate the determinant in a separate place, and then later we can compute as one. But I don't think this will work in exam, so it will take time. So I don't think I will put the 4 by 4 in exam. The most maybe 3 by 3. But you can try to find this. Take the determinant for that one. So maybe I will just write the formulations, but you can continue the computations. Okay, so let me start with the. Let me write the. This is positive, negative, positive, negative, positive, negative. I use different colors so you know that this is not the sign for the number, but rather. Oh, wait. Should be. This should be okay. So this is start with the negative, positive, negative, positive. So positive, negative, positive, negative. And then this is start with negative, positive, negative. Okay. So it should start, and the pattern should be, if you go column by column, it will change the sign. If you go row by row, it should change the sign. Every column and row, they have different combinations. Okay? So by using this blue signs, we are going to use that to determine this signs here. Okay? So I think if we use the fourth one, then we are going to have negative 1, okay? Or let me just write negative 1 multiply with the determinant of 1, 2, 4, 0, 2, 3, 1, 6, 1, right? And then the next one is 0. We can ignore, and then we plus the negative 4. So plus negative 4, so negative 4. So negative 4. This will be 5, 1, 2, negative 1, 0, 2, 1, 1, 6. Okay.
So we might need to count the determinant for each one of them and then back to the final computations and we get the formulations, okay? If you would like to try 3 by 3 just to make sure that you can do the calculation, you can try this. Sometimes for 3 by 3, I think some of you know some method. I forgot the name, the official name of the method, but it works on 3 by 3 matrix. But it is, if it is more, like 4 by 4, it will not work. So I'm usually taking this number. Let me write here. So 2, 6, 1, 4, 0, 5, 7, 3, 3, and then I will write again the first column and the second column. So 2, 6, 1, 4, 0, 5. And then the idea is I will multiply within this cross like this. So it means that I will multiply 2 with 0 with 3 with 0 and then plus this multiply 12, 1 is 12, so plus 12, and then 7, 6, 42, 5, 210. So you plus that, and then minus the left arrow, the left arrow. And then minus this this arrow. And that's also works. So you will get the determinant. But it is only work if 3 by 3. If more, it doesn't work. Okay. Sometimes I'm using this because it's faster, especially if you are able to compute really fast. This will be useful. But if you want to expand, I think this will be better. You can see the whole formulations. Okay. So this could be 2 multiplied by 0 by 3 and then plus 4, 3, 1 plus 5, 6, 7. Okay, and then minus the whole thing. Let me put this going down. Okay, let me put this down here. Then this will be 4, 6, 3 plus 2, 3, 5 plus 7, 0, 1. Okay, and then close bracket. So plus, so actually it's plus, okay, minus plus here. So the blue minus the red. The blue minus the red. The total from blue minus total from red. And also next 2 weeks we will have a quiz, okay? Matrix, okay? Only matrix, about matrix. Okay. I think until this week we are going to learn until inverse, so I think up until inverse. Okay. Okay, any questions so far? Okay, so far we are dealing with matrix, row operations, linear algebra, and hopefully we can retain all the applications, and then we are going to going back to differential equations, okay, after the matrix part. Okay, so let me continue for just a little introduction for some property on determinants, and I think some of them are important. Some of them I think you can just read it Okay, just read. So basically, first is the expansion for cofactor is actually just a normal property that is just for analyzing. But what I want to focus on is this property here. Okay, there are at least 6 property, and I don't think you need to remember all. But what you need to know is every time we deal with the determinant of the matrix,
if we transpose the matrix, the determinant will be the same. Okay? And then if all the entries in row is 0, then it will be, determinant will be 0. I think it is understandable because all the coefficients that multiply the determinant, it will be 0. The same what we have in the previous example. When we have the coefficient 0, the calculation will be 0. And then if we multiply with some non-zero real number, so we multiply a row or column, we are going to have some multiplication for that number. And then if we have the identical rows, like we have 2 rows that is identical, then the determinant should be the same because the numbers will be subtracting with each other and it will be 0. So if we exchange the rows, then the determinant will be negative. Will be negative. And then if the determinant multiply with each other with the same size, then we could just multiply each part of them. Okay? So if we know determinant A and B, and then we would like to know determinant AB, so instead of multiply the matrix and then find the determinant, you can just multiply the determinant. It will be the same. Okay? So I think that's just I think more of a trivia. And this will be, I think, will be worse if you are dealing with some exercises. So I think maybe later this week I would like to give you some exercises as a preparation for a quiz perhaps. So it's just a 1-hour quiz. Maybe I will just give you some example on a row operation and how to operate determinants, especially finding the inverse. Okay, so later we are going to see the inverse part. Okay, we are going to see the inverse part. So this is the determinants. Okay. There are some example here, but I think I will just go the example later on for the exercises. And there are some like proving, but I don't think we have time for all of that. Okay, and then there are 2 more here. If we multiply with a non-zero real number k, so suppose B is the matrix. If we multiply A with a k, and if we add the result to the entries in another row, then we could see that it will be the same determinant. And another, I think the triangular matrix, it is interesting. So let me just give example here. So let's say we have a matrix A11, A21, A31, 0, 0, A22, 0. So we have an upper triangular matrix. Okay, we have upper triangular matrix. So either upper or lower, if we would like to find determinant from this one, since they are 0, then
we could see that at the end of the day, this is going to be A11 multiplied with the determinant. The determinant is basically here, right? This one here. So this is actually from A2 to A33 minus 0 A32, right? But because of 0, we get the diagonal itself. Okay? So we just multiply the diagonal. So if you have a triangular, this or here, 0, the determinant is just multiplying the diagonal. Okay. So I think all the properties, it is based on if you play on the matrices and you see some properties will be there. Okay? This is just to show you that we have several properties, but actually the properties it is coming from if we are dealing with some numbers in the matrix. Okay. Let me see. So basically, the conclusion from this part for the triangular matrix is, if you have a matrix, you know the row operations. If you know the row operations, if you could make the row operations and make this 0, then you could find the determinant right away. So if you can see the matrix and you see the number, if you multiply some scalar, subtract, maybe some 0 will be can easily able to be solved, then you could just do this. You can just multiply the. So for example, I will just take an example from the textbook, but it's interesting. So if we have a matrix A, this is 6 to 7. Okay, let's say we are going to find the determinant. Okay, find the determinant. Okay, you could try the original way, the default way to find determinant, or we could try to go for row operations. But the way I will do this is basically, first I will factor out some scalar that is able to get here. So first I will take out, so factorize 2 from the third row from R3. So let me just write the same, 6 to 7, -4, -2, -3, and 2. And then this will be 1. And then this will be 2, this will be 4. And I would like, perhaps I would just directly write the determinant. Okay, so I will change this matrix with determinant directly. And then do the row reductions directly in determinant form. Okay, so since it's determinant from the property before, if we have some multiplication with a scalar, we could factorize the scalar. So let me factorize here. Okay. And later I will upload the notes so you could catch up with all the contents. Okay, and then I will exchange the rows. So let me write here. So interchange R1 and R3. So 1, 2, 4. This is multiplied by 2. Now, the difference is, if we take the row reductions or row operations inside the determinant, if we exchange the rows, we need to multiply with negative. Okay. So remember that there is one property that if we interchanging any two rows, the determinant will be the negative. We need to multiply with negative. So that's why this part here, since I'm going to interchange, then this will be negative. Okay. And then I will do another row operation. Let me do it to the right. So this will be so this new second row, I will add for row 1 and then plus the second row, right? So I will have 4 minus 4. So I will expect for the second row, the first column here, this is 0, and I would like to make this 0, 0, 0. I will make the lower triangle. So now this will be the same. 1, 2, 4. This will be 0. And then 8 minus 3 is 5. 16 minus 2 is 14. Okay. Plus, sorry. 16 plus 2. And then the rest will be 6, 2, 7. Now the next is we have the third row that we still have 6. So I'm focusing the 6 to go with 1. So I will make the 6 0. So I will multiply 6 to the first row minus the third row. So let me just do that. So this will be our new R3 is 6R1 minus R3. Oh, I forgot to write the negative 2 here. So 1, 2, 4, 0, 5, 18. So 6R1, 6 minus 6 is 0. 6 minus 6, 2, 12. 12 minus 2 is 10. 6, 4 is 24 minus 7 is 17. Okay. And then I would like to make the 10 become 0. So I will like to reduce that. So how to reduce is basically a new row 3 is going to be 2R2 minus R3. Okay. So we get, I forgot to write the determinant A. So all the determinant, okay. So this will be negative 2. 1, 2, 4, 0, 5, 18. And then the row 3, the new one will be 10 minus 10 is 0. And then 36 minus 17 is 19, right? And we get this determinant. So we get determinant A is negative 2, and then we compute this. And since this is having a triangular matrix, lower triangular, we can just multiply 1, 5, and 19 to get the determinant. It's negative 10, 19, negative 190, right? Okay. So the row operations, it could work with the determinant system. So if you want to calculate determinant and you would like to try using the reduction for the row, you could do this. And don't forget that every time you exchange rows, you need to multiply negative. And then if you are going to factorize in any rows, don't forget this to factorize, and then don't forget to multiply again. Because if you don't multiply with this, then you are going to get the incorrect determinant. The rest, how to reduce, is the same as we've done. We can multiply and then subtract, or we can exchange the rows and so on and so forth. Okay, any questions? Okay. I know that this matrix is the content is actually quite a lot. So I skipped many things, but I hope we can take this matrix to find our goal, which is a differential equation, like solving differential equation. So maybe after 2 or 3 weeks, we might be able to see the differential equation again. Right? Okay. Yeah, maybe in the end of this month, I think. If we have a good timing, but if not, then maybe on April, perhaps. Okay, next, after this, it is going to be the inverse of matrix. Okay. So we start by looking at the definition first. Okay, before we going into the application and how to solve using the inverse. So basically, the matrix, if we have A and B, we have matrix A, we have matrix B. If we multiply the matrix in order A, B, or B, A, if we get the same result, which is the matrix identity, then we say the matrix A is non-singular. Non-singular means it is going to be, it can be taken as an inverse or invertible. And then we can also say for the counterpart, for the B, it is going to be the inverse of A. Okay. And of course, if we are not getting this identity, then we say it will be singular. Okay, singular. We are going to see later what does that mean in terms of matrix, and it will be related to determinants. Okay, now the property for the inverse, let me just put down here. If we know that the A and B, they are non-singular, then if we have the inverse of A, if we take another inverse, we are going to get A. If we have AB and then inverse, then we can separate this, become B inverse and A inverse. And we have A transpose, and then we take inverse. It means it is the same thing as A inverse transpose, okay? Okay, so some property that is going to be sometime in a system of equations, this will be useful. Okay, now before using how to find the inverse, I think let me just go zoom out first and make it closer so that you can see the okay. Now if you look here,
We have what we call the adjoint. The adjoint matrix is if we have the matrix entry here, we take the transpose. So from this column, it's going to be the row. Okay. So every column is become row. Okay. So the last row become the last column become the last row. So we call this the method of adjoint. So this is what we call the adjoint. Now why this is important? Because the adjoint, since this is the transpose, where we can easily compute the A inverse using this formulation.
So we are going to use the 1 over determinant A multiply with the adjoint A. There are some proof here, but I think I don't have time to prove for today. But just I will just explain for a while what we have for the inverse. So basically, if we get the determinant not 0, we could surely say that it will be non-singular, okay? But if the determinant is 0,
it means it is singular, and then we cannot take the inverse. Okay. So why is that? If you see the formulation, I think it could be understandable. If this is 0, then it won't be defined. So that's why we need to make sure that the determinant is not 0. Now to find this inverse, first we need to check the determinant, and then we multiply with the adjoint.
now I think
We could take the take this 2 here. So 2, so it's 1, so 2.
so I think I will just write that determinant. So let me write determinant A for the example here. So I will take 2, and then this will, I think I will multiply directly. So 1, and then minus 2. This will be negative 2, negative 3, which is negative 5. So 10 plus 2, right? 10 plus 2 is 12, right? And then what else? So then A inverse is 1 over 12. And then we take the adjoint. So how to find the adjoint? Let me write here. Okay. So adjoint. So C11 is basically we take the one 101. Let me just show you all, or maybe this is 21, sorry, 21. 21 is -2, 2 0 0 1 and negative. Two 0 1 1. C12 is -2 3 1 1, which is -2 -3, and then negative, sorry, -5 negative, so 5. And negative 2 2. 2 2 is 2031, 2031, and then should be the sign the same what we did before, the pattern for the sign, and then C 3 2. Let me just solve this first, okay? 2 0 3 -2 1, and then C1 3. Okay, 2 3 is 2 2 3 0, and then 3 3 is 2 2 -2 1. So 2 plus 4 6, right? Is it correct? I think it should be correct. And then we are going to adjust this, all this determinant result in transpose position. So 1 -2 2 5 2 -2 -3 6 6, and then multiply, and that is our inverse. Okay, so I think I will continue later on this Friday.